Okay, so it's very difficult sometimes to wire up these logic chips for the first time, mostly just because there's so many connections. But the nice thing about logic is that you can go through it piece by piece and really build it up in modules such that the whole thing makes sense the entire time. So let's do that. Let's wire up our logic circuit. Here we're going to use a D-Latch flip-flop or a data latch. And the way this works is that when the clock is high, when the switch is what we call the clock, and when that is high, it's going to listen to what's on the data. It'll transmit data through to the output Q. Q bar here is just the inverse of Q. So if it's 1, then Q bar is 0, and vice versa. So what else do we have? We have the data here. Data, or is it D? And the data is what's getting transmitted. So if the clock is high, that data will just get through. And as soon as we set the clock low, it's just going to latch onto whatever value it happened to be at. And then it's going to ignore data. So this is actually a 1-bit memory device. When the clock is high, it listens to data. You set the clock low, and it just stores whatever value is held in data. So we're going to build one of these things. And in order to do that, we have to kind of systematically go through it. So the first thing to note is what we're actually going to use. We're going to use this quad NAND gate. It's a 7400. Unfortunately, it doesn't say 7400 on it. It says SN74HC00N, but 7400 is somewhere on there. So we'll get it in there. And sometimes these legs are a bit wide, so you kind of have to push evenly on the table, and it should fit right in. And then we can access pins 1 through 14 by these rows here. Okay, the first thing we're actually going to have to do is put our inputs. So let's make our inputs here, which will just be switches. Now, according to the data sheet of the 7400, anything between 3 and 7 volts are good for powering this thing. So we can use either our 5 or 3.3 volt input on the board. We'll use a 5 volt one, and we'll make, first of all, our clock here. So these are a bit stiff to fit in, but eventually it works. And what we'll do is we'll put it either at ground, or 5 volts. So here's 5 volts here, and ground. In fact, I'm going to do it the other way, so that this position, which, I don't know, to me psychologically seems like an off position, corresponds to off. So put the ground here. What do we do? Let's actually get a good color scheme going here. So we'll let white be ground. And black wires can be positive. Why not? And the middle pin should be 0 or 5 volts, depending. Now we need to verify that somehow, so let's put a little visual indicator here. So what we're going to do is we'll put a LED here, and that's merely just going to tell us the value of the switch, on or off. So we'll do that. It's currently off, and it's on. So we can go on, off like this. Let's do the same for that was the clock, rather. Let's do the same for the data. So this also has to be at 5 volts in this position. And ground. Okay, and we'll put an indicator as well. I guess the data is green as we've drawn it, so we'll keep a green LED for that. And that should indicate the value of the data switch. So it's on or off, and clock can be on or off too. So that works. So we can set these two bits. These are basically the two bits that we've allowed us to gain access to. It'll help to have a indicator whether or not we have a logical true or false that we can use to probe later on in the circuit. So let's do that now. Let's just put this to a given resistor, and anything we plug into this row here, this blue LED here will light up to tell us whether or not it's true or false. So we can already test our positions here. So let's do that. Make sure it works. On, off, okay, good. And off and on. Just plug that in there. Good. Okay. So we're just going to leave this hanging here so that we can probe what the value of logic is at different parts in the circuit. Okay. So here's our two inputs. Let's just leave them out here. We have our clock input and our data input. And that's going to be our data that we can send in, and the clock telling us whether or not to send data, whether or not to pass it through. Now we have this circuit diagram. This is the topology of the data latch flip-flop, and it's hard. It's a bit difficult when you're just wiring it up because things get messy very quickly. And what I find helps is we'll actually put the physical pin numbers. So for example, chip 1 here has 1 and 2 at its input, and its output is 3. The second NAND gate here has pins 4 and 5, and 6 is its output. 7 will go to ground. This will go to 5 volts, pin 14. And let's keep going. Op amp 3 has 9 and 10 for its inputs. And the output is pin 8. The output of pin 4 is 11, and 12 and 13 are its inputs. Okay, great. So we don't need this anymore. This is our from the data sheet what the internal workings of this quad op amp are. So let's continue now. We'll start wiring this thing up. And basically what we've done is we're going to break this up into modules. We just checked that the data inputs and the clock inputs work. Let's actually just test one of these NAND gates to make sure that that works. We'll get a check mark there. And we're going to build this up in stages and make sure that it works at every step of the way. That'll make debugging a lot easier when things go wrong. So first of all, let's just check to make sure that we know what a NAND gate does. This is actually kind of illegible here, so this is 12 and a 13. I apologize for that. So that would correspond to these pins here, 12 and 13. And the output is pin 11, which we're going to put to our indicator. All right, so 14, 13, 12, 11. And as we mentioned, we have to give this thing power. So pin 14 is going to be 5 volts. It works even with grounding it, but I wouldn't count on that. And pin, let's try to keep the same color scheme. If I have one more white cable. Pin 7, we said, was ground. Excellent. So, NAND gate. What is a NAND gate? NAND is the following truth table. 0, 0 should go to 1, and everything else, oh sorry, wrong. 0, 0 should go to 0. 0, 0 should go to 1. It's not and. 0, 1 should go to 1. 1, 0 should go to 1. And 1, 1 should be the only thing that goes to 0. So here we have 0, 0. That went to 1. 0, 1. 1. 1, 0 goes to 1. And 1, 1 goes to 0. So this thing works as a NAND gate. Great. So we actually have NAND gates. We're getting power. That's all we're checking there. So now let's start, interesting, let's start wiring this up. And what we'll do is, what I find is very helpful is to kind of mark the path along the way. I'll show you what I mean. So we have this switch to the data. It's going to be going to pin 9. So this is 8, 9. The clock is going to be going to pin 13. Whoops, we already have a wire for that. Like that. So we'll wire that in here. That clock is also going, that same part is also going to pin 10. So here's 13. We have 8, 9, 10. And that one is now done with the yellow wire. Okay. At this point, we can actually check that our NAND gate is working for this part of the circuit. So if we look at pin 8, that should be our output. It should be giving us NAND of the input, which it indeed is. Excellent. So pin 8 works. That's good. Where is it going? Well, if we see this, we're going to send that to 2 places. We're going to send it to pin 1 and pin 12. So here's 8. It's going to be going to pin, let's see, let's go 8, 9, 10, 11, 12. I need an orange one for that. That one's done. And also to pin 1. So let's go 12 here to pin 1. And that works. Okay, a few more wires to go. The output, pin 3, is going to go to pin 4. So here we go, 3 to 4. And we'll wire it this way. And at this stage, can we? We actually can check that pin 11 is working. So we haven't given this a check mark yet. I forgot to check pin 11. Let's do that. So that should be only if the output of 8 is 1, which is when 9 or 10 is 0, or both, or if the output of 8 is 1 and the clock is 1, it should give us 0, otherwise it should not. It should give us 1, so let's go to have a look at pin 12 here, or sorry, pin 11, 8, 9, 10, 8, 9, 10, 11, there it is. So that gives us 1, and there's one circumstance where it should get 0, which is indeed the case. When this one is 0, it gives us a 1 and a 1. Okay, so this actually works. I'm confident that everything is correct up to here, so we only have a couple more stages to plug in. And this is really, I think the best way to do this is to do it kind of systematically this way. So next let's wire up 5 and 11. So we got 7, 6, 5. And 11 is what we just checked, right? That's this one here. So let's pop that out. 11 is what we just checked. So we got 5 and 11, check. That green wire there. And we have one more cable before we start looking at our outputs. That is 6 should go to 2. Let's make that red. So here's pin 6, and that goes to pin 2, and we should in principle be done. But we have to indicate. So what is Q in Q bar? So in order to see whether or not this works, we'll put this to our blue indicator. And to do a sanity check, we'll check that Q bar is always opposite. We'll let that be a red LED. So let's get one more indicator here. With a red LED. And they should be opposite. When one's on, the other should be off, and vice versa. And we'll wire it up. So let's get this 6. We're into the red. All right, I hope the blue turns on, because that would be an indication that it actually works. But it might not, and that's good. That'll be a good chance to debug a circuit in real time. Okay, that's good. So far so good. Now, I don't know if this works or not yet. What a data latch should do, here's data, it should ignore this value. Okay. It ignores the value because the clock is low. Good, so far so good. Partial check mark. Let's set the clock high. Now it flipped. Uh-oh. Wait, does that make sense? It does, because the clock is now passing through whatever value is in green. So it should be just passing through that value. Indeed, it is. And we should be able to store values too. So we're passing through value. Let's say we want to store a 1. That's blue here. Let's store a 1. So we set clock to low. And it should basically just ignore what's going into my input now. It's hard to see my finger in the way here. But basically, if you see that, it's ignoring the input. So we'll set the clock high again, and we'll store a 0 now. Store a 0 instead of a 1. Set the clock low, and it ignores all inputs. So we have a D-Latch circuit. And that's how you wire this thing up. It's good to do it systematically. Now, of course, that's when everything goes right. What if things don't go right? I don't know how we're going to do this, but let's just try something. I'm going to plug in, what's this here? 14, 13, 12, 11. Let's plug it in by accident. Let's plug that to 12 instead, next door. And we're going to get some funny behavior. Okay. I don't think it's going to work anymore. I don't know how it's not going to work, but let's find out. So clock is low. It's ignoring, that's good. Clock is high. They both went on. So that should not happen. So what happens when you get a weird state? Well, you can debug it. You can debug it by going through and seeing what it should be doing. So if this circuit is correct, we should never get 1, 1 here. So we're sending in 1, 1 and we're getting out 1, 1. Let's find out where it goes wrong. So what we'll do is we'll plug in 1, 1 to here and find out what it should be doing and see where it's going wrong. So if we have 1, 1 here, that should give me a 0. And that goes to this one here. That goes to Q. And this is just my output. This also goes down to pin 2. And this output goes like this. Basically just copying the schematic here. Okay, so what do? We set it to 1, 1. So that means we put this is equal to 1, this is equal to 1, and this is equal to 1. Let's see what we should get. Oh, and I forgot a wire, didn't I? Okay, so if this is equal to 1 and this is equal to 1, this is going to be equal to 0. If this is a 0 here, no matter what this thing is, this is always going to be a 1 based on this NAND gate here. If there's any zeros, it's going to be a 1. Okay, so I get 1 here, and I have 1 here, I have a 0 here. Because I have a 0 here again, no matter what is happening here, I'll always get a 1. And if this is a 1, and this is a 1, this should give me 0. But that's not what I see. I see a 1 here. So we first probe at what's going on with this gate here. How do we do that? Well, let's just get our multimeter out. Things don't always go right. Let's try to debug this situation here. Okay, so this is a suspect pin here, which has, it looks like 5 and 11 at its output. So let's see what it's putting out. Pin 6, 5 volts, that's true. That's what we expect from there. But pin 3 is also 5 volts. And that means that this thing is getting 5 volts here. So pin 11, pin 5 here, where's pin 5? 5, it's getting 0. But wait a second, shouldn't that be getting 1? Thought that was connected. Where's that 1 coming from? Pin 5 is connected to pin 11, so we look at pin 11 and uh-oh, there's nothing connected to pin 11. What happened to pin 11? Well, we look at it and that should be connected to pin 5. Well, pin 5 is it's connected to pin 12. So then we fix that. Before debugging everything else again, let's just check if our problems are magically fixed. In this case, they are. So when things don't go wrong with a logic chip, all you do is you figure out where it should be working. You find the latest, you work backwards, finding the first part where it stops making sense, and then work backwards this way, and you can debug the entire circuit that way. Okay, and that's a quick tutorial, or not so quick tutorial, on how to wire these things up.